Let's look at the Ka and pKa with an emphasis on organic molecules. So let's refresh what the Ka actually is before I get to some values down here. So we have some acid plus water, and that's in equilibrium with the conjugate base. And H3O plus. And if we were to write the Ka expression for this, which is just the equilibrium constant expression for this equation, and for now, let's assume that we're working in dilute solutions, so we do not need to worry or think about activity. And there we have the expression. Now, we should examine this a little bit so we can understand what is happening with our Ka and pKa values. So if an acid is stronger, it will be able to protonate more water. So it will push the reaction more towards the right. That means that we would have more products versus reactants. So a larger K means that it's more product favored. So if we have a K that's significantly bigger than 1, then the reaction's product favored. If we have a K very tiny, like it's still bigger than 0 because K's can't be less than 0, but much less than 1, close to 0, then the reaction is reactant favored. And these K's can vary over a wide range, going all the way from somewhere around 10 to the 25 down to 10 to the minus 50, depending on which compounds you're looking at. And since this is a very big range, we like to use logarithmic scales for things that have a very long range. And the formula that we came up with for this is using the pKa. And the pKa is just the negative logarithm of Ka. So since there's a negative here, it changes the sign. And so if the pKa is small, that means that the acid is very strong, since we put a negative sign in there. I wasn't in charge of that decision. So a lower pKa equals a stronger acid. And because we have a stronger acid and the acid is correlated with the conjugate base, that will mean a weaker conjugate base. Now, conversely, if we have a very weak acid, then we will have a very strong conjugate base. So those go kind of hand in hand, but they're opposite of each other, right? So stronger acid, weak conjugate base, weak acid, strong conjugate base. All right. And because of the logarithmic scale, if we change 1 unit in the pKa, that's a 10 times change in the strength. All right, so now that we've laid the groundwork, let's talk about some pKa values that we may encounter when we're looking at organic chemistry. So for reference, and because we do use sulfuric acid in organic chemistry and also hydrochloric acid, some of these things, let's look at this. So here is the acid, and there is the conjugate base. And this has a pKa value of around -9. So this is a very strong acid. And you probably have learned in general chemistry that sulfuric acid is one of the strong acids. So that fits. A very small, so a low pKa, strong acid. And these are going in order here. Hydrochloric acid is a little bit weaker than sulfuric acid. It's about 100 times weaker. I suppose that's a little bit. Now we get up to some organic acids. So this is a carboxylic acid. And depending on what we have over here on the R group, we can change its acidity. But unless we're putting a lot of electronegative things over here, this will be approximately 4 to 5, somewhere in that kind of range. And this is +4, so I should say approximately +4, because I don't want that to look like a negative number, to +5. So these are much weaker than our strong acids. We come to our nitrogen compounds, so ammonium or other nitrogen organic molecules. So if we were to change this to, like, say, NH3 plus, and then had some organic molecule over onto the side here, these are similar to each other, but for the ammonium, it's 9.4. And for some of these, it would be slightly different, but around 9 to 10 is somewhere in the range for the amine type molecules. We have phenol is about 10. So this isn't a really great acid, although you would not want to get this on you because it will burn your skin quite badly. Just because it's not the best acid doesn't mean it can't do some damage. We have alcohols. So this proton here on an alcohol can come off, but depending on the substitution on the alcohol, we can have somewhere around 12.5 all the way up to about 19, depending on what is on this R group. So there's a little bit of variability there, but it's somewhere in that range. Water has a pKa of 14. There are a lot of organic chemistry textbooks that say that this is something other than 14. That is not correct. And if you do the proper thermodynamic calculations, you will arrive at 14. Now we have a ketone with its alpha hydrogens. So if we count one carbon away from the ketone, we get to the hydrogen. And if we remove one of those, the pKa for those hydrogens, so how acidic this is around 20. So we're getting to pretty weak acids, and under normal circumstances, we may not consider these to be acidic. But if we use stronger bases, we can get them to come off. So here's an alkyne, and if we have a terminal alkyne, so an alkyne at the end, we can pull this proton off, but that takes, it's 25, so it's not very acidic. Hydrogen is 35, so very not acidic. And then we come back to a nitrogen-based compound, but this time we're taking off that proton. Before we did it over here, this was a positively charged one. This one had an extra proton on it. We are pulling off the proton and making it negative. That's hard to do. So this is 38. Even harder to do is to pull a proton off of this carbon-carbon double bond, right? So right next to our sp2 carbon, we pull one of those protons off. That's about 44. And then a fully saturated hydrogen, pKa of 50. So very, very difficult for this to be an acid. Now, let's think about this in the other direction for bases. If we were to somehow make a carbon with a negative charge on it, and it was an sp3 carbon originally, this would be a very good base. One of the best. Since it's such a weak acid, since this is very weak for it to come off, conversely, that translates into an extremely strong base. So these are very reactive. They will take off protons of other things. Anything further up the list, this will, if we have this species here, it will take the proton off. Same thing here. Very basic. This is also very basic. Very easy for this to pull a proton and go over to this molecule. Because remember, this proton really does not want to come off. It's got a pKa of 38. That means it doesn't want to give up the proton. This is not an acidic compound. Hydrogen, similar way. When we get down below here, it's not too hard to take those off because we do have compounds like hydrides, like for example, NaH, that can easily deprotonate an alkyne, a terminal alkyne, or some of these other molecules up here. Just don't expect adding a chlorine in will do anything to the acid-base character of anything over on this side of the table that I have. So that's just looking a little bit at the Ka and talking through, like, larger K means it's more product favored, which means it's more acidic. A larger K, because of the negative, translates into a negative number here, which means if it's a lower pKa, it's a stronger acid. A higher pKa means the conjugate base of that acid is a strong base. Right? It's a mouthful there. But and this is how we use this. And so it's a good idea to have a general sense for what the range of these Kas and pKas are, so that it's easier for us to understand what will happen when we're conducting reactions that are transferring protons around. And so with that, I'll see you in the next video.